Welcome back to my channel. In our last video, we started to talk about 01 knapsack for the case where we can pick one item multiple times. Just to wrap up that last video, we said that from our dynamic programming, we get a table, and in that case, it's a one-dimensional table where you have the array giving you the max I from 1 to a given n, so I just wanted to mention real quick that the base case, our base case is always going to be 0, and that's because at our start point our weight is 0 and the value is 0. So our base case is always going to be this equals 0. So for our table, this is our base case where weight is 0. So weight equals 0, value is 0. Then we progress from here. And this value, this A of W, where W is the weight, you should interpret it like index, where W should be the index with the index that has the largest value. So that should round it up for the 01 knapsack, where you select one item multiple times. I already gave an example. So for today, we'll be looking at the 01 knapsack where you select an item only once. But the problem with this case is that we want to encode our choices such that we avoid repetition. So the question is, how are we going to solve this problem without picking one item more than once? So the first thing we do, let's quickly get this off. So the first thing we do is we arrange the items in descending order, if you may, or in ascending order. So you want to sort the items first. You might be asking, why are we sorting the items? And like I said, let me just reiterate. For the 01 knapsack problems, we have two kinds. We have the first one we already talked about in the previous video, where we can pick one item multiple times. And bearing in mind that our goal for the 01 knapsack is to fill up our sack with the items that have the most value. The second kind of 01 knapsack problem is the kind where we have a restriction on how many times we can pick an item. And in this type, we can pick one item just once. And the problem when solving the 01 knapsack, where we have to pick one item once, is that we have to devise a means for not repeating items. So how do we know, or how can we stop ourselves from picking an item that we have picked before? So to do this, like I was saying, we sort the items first. We want to sort it in some order. Let's say from 1, 2, 3 up to n, and we start from picking from one end. Let's say we start from picking n. So when we get to n, we decide whether we want to pick it or not. Then we get to n minus 1, we decide whether we want to pick it or not. We continue in that way until we get to 1. That's this item. Let's put it down like in recursive form. We have knapsack, where your knapsack capacity is this big W, and you have n items. So let's start. We're looking at the nth item now. Pick or not to pick. Supposing we pick, this is yes. Supposing we pick, it means we have taken the value of n plus what's left is the knapsack of W minus Wn. That's the weight of this n that we have picked. N minus 1 items are left. And if we do not pick, we are left with knapsack, still the full capacity because we haven't picked anything. But now we are considering items from n minus 1. Then this goes again, the same thing. We pick, yes, or not to pick. So if we pick this n minus 1 item, it means now we have Vn plus Vn minus 1 plus what's left. We have K W minus Wn minus Wn minus 1 n minus 2. And if we do not pick, it means that at this point we have Vn plus K, the capacity still remains same because we didn't pick, but now we have n minus 2. And the same thing happens here. We decide, do we pick or not to pick? So in case we pick yes, we don't pick no. And if we pick, if we say yes, it means now we have, in our sack we have Vn, that's the value of n minus 1, plus now the capacity, we have W minus Wn minus 1 remaining, and n minus 2. And if we do not pick, we have this capacity still full, and n minus 2. So we are going to continue like this, keep going this way, pick or not to pick, yes, no, yes, no, yes, no, until we get to the last item. And if you noticed, this diagram looks like it's, in fact, it's a recursive substructure. It's we have drawn this diagram to show the choices we have made, and to cross out each item after we've made a choice concerning it. If we picked, then we can no longer, if we picked, let's say n, we can no longer consider n down here anymore. If we picked, let's say n minus 2, we can no longer consider it down here. So that's just what we've done. So let's write this down. So this can be written this way: the knapsack that has a full capacity of W and J items, it will be the maximum. Remember, the objective for when you solve a 0-1 knapsack problem is to fill your bag with items that have the most value. So we want to choose the maximum of whatever we have chosen. What's left is this. Or if we did not choose this, we have this. So I need you J minus 1. I hope this makes sense, and this is exactly what we have here. So for the sake of simplicity, we defined what the value of our knapsack should be from this point, just for the sake of simplicity. We want to find the maximum. If this, between this and this, we want to find the maximum between this and this representing the value of everything underneath it. So supposing this is our leave. Let's say this is our leave. We want to choose the maximum. So we go either this or this. This is what this formula says. So let's define the base case. Just as I said, concerning the 0-1 knapsack for repeated items, here too, our base case is going to be 0, meaning we have no item. So we have our base case 0 because we have no item at first. When the weight is 0, we have no items yet. So when we have drawn the recursive substructure for this problem, Next thing we do is we use dynamic programming. And for the dynamic programming, it's the algorithm will fill up a table that looks like this. This table is going to look like this. You have going from 0, 1 to all the way to the capacity. These are the weights, WI. So we start from 0 weights. And these, you go from the items. So you have 0, 1, 2, all the way to J minus 1, then J, then N. So these are your items. And at this point, this is where you will have your answer, because this is where you will have the greatest value. And as we can already see, when we attempt to fill up this table, when the weight is 0, we have no items, value is 0. For weight 0, well, there is no such thing as one item with weight 0. So everything here automatically would be filled up with zeros. Here too, we have no item. No item, all the weights will be 0 for no item. So we're going to, proceed that way until we fill up the table. And the complexity for this table, time complexity, it's going to be O. This is W, the capacity. So as we fill up the table, we just access the values from previously filled cells of the table. And this leads us to this, where A is our array or our table for a particular weight and a particular this. We have just as we showed in the table, the weight goes from 0 to the capacity, and J is the item, and it goes from 0 to N. Let's just put that down, where this goes from 0 to the capacity, and J goes from 0 to the number of items. Defining our base case, just as we said, this is our base case. Weight 0, item 2 is 0. This is our base case, and for this base case we have 0. This is also a base case. J, this will give us zeros. Weight but no item, this gives us zeros. So we're also going to include our algorithms here. So for W equals 1 to the capacity, and for J equals 1 to the number of items, we have for this and for this, if a particular weight, the weight of J, exceeds the capacity, exceeds or is equal to the capacity, in this case it can only be equals the capacity. So if this is equals the capacity, we have this maximum of, that's the formula I had given you earlier, J minus 1 if chosen, or if not chosen. So you have the capacity intact, J minus 1 if not chosen. Else, that is when weights are less than the capacity, else we have AWJ equals AWJ minus 1. We're going to end this video here. If you like this video, remember to subscribe, like, and comment. And I hope everything is very clear, pretty much clear. In the next video, we'll take an example on this topic. So